Welcome to the video on acceleration problem solving. As a review, acceleration is the rate at which velocity changes. Objects accelerate when they speed up, slow down, or change direction. Acceleration is the rate at which velocity changes, which means the change in velocity over the change in time. Remember, we use this A for acceleration. And those triangles are deltas, or change in. So acceleration is also equal to the final velocity minus the initial divided by the change in time, or the time interval. So just as we had x sub f, for example, for final position, v sub f means final velocity. V sub o means original velocity or initial velocity. When discussing the units of acceleration, we take in mind that the units of velocity are meters per second, the units of time is second, so the units of acceleration, velocity over time, is a meter per second squared. Please note that our equations from earlier in the year, such as velocity is equal to displacement over time, is not valid when an object is accelerating. This equation is for constant velocity only. Here's an example problem. The BMW M3 Hardage claims to accelerate from 0 to 60 miles an hour in 4.4 seconds. According to the advertisement, what is the acceleration of this BMW in meters per second squared? So we list our knowns and our unknowns. We know the initial velocity is 0 miles per hour. So v sub o is 0 miles per hour. It reaches a velocity of 60 miles per hour. That means it's the final velocity. And this occurs over a time interval of 4.4 seconds. For the unknown, we're looking for the acceleration, A. The next step is always to draw a picture. For these acceleration problems, you should always have 4 total knowns and unknowns that will be present on your picture. So here's the car. With an initial velocity, it starts at rest and then accelerates quickly to a final velocity of 60 miles an hour. This occurs over a time period t, and the object is accelerating. I'm going to draw that arrow on top of the A to show the direction of the acceleration. So remember, if the object is speeding up, the acceleration and velocity arrows should be going the same direction. The next step is to choose our standard equation. Acceleration is the change in velocity over the change in time, which means acceleration is equal to the final velocity minus the initial velocity over the change in time. We're almost ready to plug in our known values, but looking at our list of knowns, we see our units don't match. Our velocities are in miles per hour, while our time is in seconds. And the problem specifically asks for the acceleration in meters per second squared. So we need to convert our velocities to meters per second. So for the initial velocity, it's simple, right? 0 miles per hour is the same thing as 0 meters per second. An object at rest is at rest, no matter what the units of measurement are. Now we can convert 60 miles per hour to meters per second with the factor label method. For every 1 mile, there are 1,609 meters. Notice how the miles cross out. For every 1 hour, there are 60 minutes. And for every 1 minute, there are 60 seconds. So note how your final units are meters per second. So you should type this in your calculator along with me. And let's see how many meters per second we get. This comes out to be 26.8 meters per second. Okay. Our knowns are now in the correct units, so we can say our acceleration is equal to 26.8 meters per second minus the initial velocity, which is 0. So we can really just cross that out in our equation, divided by the change in time, 4.4 seconds. This gives an acceleration of 6.09 meters per second squared. This acceleration is to the right, so it is a positive. Acceleration is a vector, so please include your direction. We have one more example to do together. A man is biking with a velocity of 10.3 meters per second when he sees a deer on the trail a few meters ahead. He presses on the brake and gradually comes to a stop with an acceleration of 2.32 or 2.3 meters per second squared. How long does it take the biker to stop? We'll list our knowns and our unknowns. The initial velocity being 10.3 meters per second. The acceleration is 2.3 meters per second squared. We're looking for the time because it says how long. There's one more known in our problem that may not stand out, but it says he presses on the brake until he stops. So a stopped object has a velocity of 0 meters per second. We then draw our diagram, right? Our biker has an initial velocity and he's moving to the right to come to a stop. This means that he was slowing down and his acceleration must have been leftward. Notice how the directions of those arrows do not match, so the man is slowing down. Looking at our picture, we have a leftward arrow. So we need to add in a negative to our acceleration in our list of knowns. Right? If the velocity is positive and the acceleration is negative, he can slow down to that stop. Next, we choose our standard equation. Acceleration is change in velocity over change in time. So acceleration is the final velocity minus the initial velocity over the change in time. Our final velocity is going to be 0, so we can cross that out we now have acceleration is the negative initial velocity over time. And remember, we do our algebra first to solve for time. We multiply both sides by t. And we're almost there. We need the t by itself. So we'll divide both sides by a to come up with the equation that time is equal to the negative initial velocity over acceleration. We can now put in our knowns. Excuse me, that was the acceleration. Initial velocity should be the negative 10.3 meters per second. Divided by the acceleration of negative 2.3 meters per second squared. Notice how the units are staying in when we plug in our values. And this brings us to a final answer of 4.48 seconds to come to a stop. Our answer for time makes sense because it's positive. If you ever have a time answer that comes out to be negative, that wouldn't make sense, and you would know you've made a mistake and need to check your work.